All right, going to our notes for today, we're going to talk a little bit about the science of sound, kind of get the sense of where sound waves and things like that work, everything like that. Let me throw the obligatory family picture in there just so you know I'm relatively normal. This is my wife and my boys. Kirk is there on the far left with the yellow hat. He's not in Paris anymore. That picture was taken right in front of the Eiffel Tower. But he is a senior, just started his senior year at NYU, living in Brooklyn and New York. So he's like a lot of you, junior, senior, trying to wrap up and get on to his life and career. My son Garrett is there in the brown jacket, light brown, and he just graduated from high school, but he's decided he's going to take a gap year. So he's working like crazy at Target and putting in the hours, making some money before he goes to school next year. Got a couple schools. He's thinking like he'd like to go to New York again to be with his brother. He also is looking at University of Colorado, Caitlin, so he might be out your direction as well. So, and then my youngest son, Jude, there in the black sweatshirt, he just started his junior year of school, and he's at an arts academy, arts magnet school over in Arcadia area. So he's here in the area as well. So, all righty. So following along, talking about our sound waves. Sound waves are going to be three-dimensional. One of the tricks and one of the great challenges with sound waves is that we can't see them, right? We talk, the famous Billy Graham statement, you can feel and sense the Holy Spirit, but you can't actually see the Holy Spirit, right? You may have heard that. It was on a DC Talk album many, many years ago. Same idea when you talk about sound waves. So my voice is talking. You're hearing it through speakers and microphones and stuff like that getting to you. If you were here in the room with me, you would hear those sound waves as well. You could clap, you could scream, you could jump up and down, you could hear a car outside. All those different sounds are being created. These are sound waves that are being created. And they're all three-dimensional. So they have a width, a height, and then also a depth as they move out into the air, and basically sound pressure, as you might talk about. A few examples you could think about is like you may have this summer been at a lake and taken a rock, or done this at some point, and you throw and you see as that rock skips across the water, you get those little divots, right? And these little concentric circles start developing on the surface, so you've seen that. You also may have seen visualizations like in water, in the wind sometimes. Another good example would be as if you're looking at different recording technologies or software packages and things like that. Like if you use a program called Final Cut, you might see a picture that looks a little bit like this. This is a video that I did just recently. Make sure that you're seeing that, jumping back and forth here. So this is just a screenshot taken recently from a video I did just a couple days ago. And if you look at this with me here, I'll get my telestrator working here. And you look in this segment here in the bottom, this very small area here, basically this line going all the way across this whole section here, you'll see both the video feed on this timeline, but you'll also see these different blue sound waves and things like that. And that's a representation of what a sound wave may look like as you go through that. Now, a sound wave is going to be relatively complicated, but for our purposes, we're really going to talk about it in a simple way. First of all, the idea of a sine wave, which is kind of the most basic waveform. And then after we have a sine wave, then we have more complex, which would include things like overtones and fundamentals and all kinds of stuff like that. Notice on the left we have relatively simple, and then as we look at the right side of these pictures, they're getting more and more and more complicated. And again, that's what we would see as we go back to this picture from Final Cut. These visualizations here at the bottom, if you're ever editing a video, you can kind of get a sense when a sound or when a speaker is starting. And if you look at the end of this video, which I can't do here with you, but you would see that that's where the end or where the quiet is happening as you move forward on that. Does that make sense? Any questions? Awesome. We'll keep moving forward here. So the overtones create a spectrum of additional frequencies that are present in all these different sounds. Now, the sounds we hear are normally made up of a mixture of different sine waves. Let's get our picture of our sine wave here again. That combine together to get more and more complex to create the unique mixture of sine waves, which create the unique tone, or sometimes you hear the word timbre, of different instruments or voices. Now, this mixture of sine waves creates the unique characteristics of each one of our voices, also creates the unique characteristics of each different instrument. So these are the reasons why a guitar might sound different than a flute, or your voice may sound different than my voice, right? Our brains and our ears really have the ability to recognize and recall lots of different unique instruments and sound characteristics, these sine waves. So think about a couple of things. First of all, if you ever, for the first time you ever talked to somebody on the telephone, right? Nowadays we have caller ID, right? That helps us a lot because we pick up the phone and we know who's calling. But we still have times like somebody may call us from an odd number, and you all know that feeling, right? Like, I don't know who's on the other end. It may think about a second. You've also had this one where the voice on the caller ID doesn't match the person on the other end, right? You ever called mom or called your dad and mom picked up the phone? You're like, hey, mom, why are you on the phone, right? Our brains will recognize that. Our brains have a category, like a library of sounds that we recognize, including family members, including famous movie stars and sports athletes and stuff like that, even cartoon figures, right? So let's watch a real quick video and get a chance to watch. Did you know that the person who voices Bart Simpson is actually a woman? Did you know that? A few nods, both going both direction. All right, let's play this real quickly here. Can you see that? You're not hearing it though? All right, let's do this real quick. All right, let's try it one more time.
Your attention, please. Your attention, please. I have an announcement to make. I'm bored.
Ha ha! You think you're bored? What about all those poor suckers out there in the audience?
Ah, yeah. They just keep praying that their category is next. Well, as long as they are praying, and while we're at it, I get to anoint their feet.
You keep your hands off me, you little twink, or I'll call the cops.
My daddy's a cop. His breath smells like cat food. And that, my friends, is how I make a living.
So a simple little video, but you just get some sense. There are lots of people in Hollywood and actors that make a huge living by being voice actors. That could be a career path for somebody if you're ever interested in that. But the ability to change and manipulate and alter your voice. And also think about this a second. We anticipate when we think about the character Bart Simpson, we have a picture in our mind of what that should be, right? We think it's probably a male. We think he's probably less than 14 or something like that. We expect certain things in our head, and then we actually see the visualization of what that looks like. There's another fun video on YouTube where like a 13-year-old kid met that actress. He was like delivering pizzas or something like that, and she answered the doorbell, and she did the whole thing in Bart Simpson, and he's like, wow, you really do that well. And she finally revealed, like, it's me, it's Bart Simpson, it's the same person, and how surprised she was. So let me ask you, what are some famous voices, what are some famous noises and sounds that you would recognize?
SpongeBob SquarePants.
SpongeBob SquarePants is a great one, yeah. Other cartoon figures?
Pikachu.
Pikachu, yeah, that's a good one. That's right. That's right. Of course, there's lots of YouTube videos nowadays where you can kind of watch the behind the scenes, you know, as different actors. Who played the part of Marty?
I think Chris Rock.
Oh yeah, there you go. Chris Rock. Chris Rock has done lots of different voiceover work over the years, for sure. Sometimes if you don't know who the voice is and you're kind of listening, you're like, I wonder if that's, you know, you kind of visualize and picture in your head who that might be. What about famous people? What about like, anybody think of a politician that maybe like if you heard their voice on the radio and you didn't visually see them, you might recognize them right away? I know, we're half an hour to class, I'm already talking about politics. Here we go.
I'll break the ice. We'll go with Donald Trump.
That would be a good one. We could just say generic, the President of the United States, right? I bet just as quickly if I played you a recording of the previous president, you would probably recognize his voice or his wife's voice. We've heard their voices so many times, just like we may have heard a parent or a sibling's voice, that our brains can categorize that. And then there are people that make a living as voice impersonators, right? Comedians that do voice impersonators, and they will try to sound like a particular person. There's several famous ones on Twitter right now of people mocking current presidential candidates and different things like that. What are other famous people? Maybe there's an athlete that you really, really, really like to see play a game, or you would recognize their voice when they come on the radio. Like if I said LeBron James, would you recognize the voice of LeBron James? No? Girls, what about singers, favorite singers? Like if we played something by Beyonce, would you recognize Beyonce's voice right away? Oh yeah, maybe a worship leader that you really like. Other famous noises and voices that you might know.
Jim Carrey.
Jim Carrey is a good example. Can you give me another something that was distinct about Jim Carrey's voice, or something that you really remember?
It's more like the tone of the personality rather than the actual voice. There's a certain energy that goes along with it.
Yeah. With musicians and singers, I mean, that's one of the things that a lot of marketing people will tell us, is that there's something unique about their voice. You'll hear that a lot of times. There's something unique about their voice that kind of sticks in your mind. So if I said Beyonce, or I say Bob Dylan or the Beatles, I mean, you may recognize the songs, but you really may recognize those voices and things that are characteristic in your mind. You recognize the difference between a male voice as opposed to a female voice. And our brains and our ears fit so much into this sound wave quotient as we talk about this. So awesome. All right, so today we are going to talk about 5 different factors as we talk about sound waves today, and those factors include amplitude, wavelength, period, frequency, and speed of sound. So again, amplitude, you may have heard a lot of these words. Wavelength, period, frequency, and then finally we'll talk about speed of sound as we go first into this long process. Now we've got a picture here just real quickly of a sine wave. I can follow along here with my little telestrator as we go through. There's highs and lows as they go through the time. Now notice on our graph, as we're talking about math today, the vertical axis, the vertical axis is for amplitude, and it's not on here, but the horizontal is referring to time, the passage of time as we move forward on that. Now, we're going to learn about the speed of sound, that the speed of sound is basically 1,130 feet per second. Now, for our examples and everything we're going to be doing here in class, this is kind of our key number that we're going to be used. But do recognize that the speed of sound actually is relative. It will change based on any number of factors, including temperature, humidity, atmospheric pressure, and different things like that. We also know that the speed of sound, this number 1,130 feet per second, is the speed of sound when we're talking about air, so passage and moving through air, as opposed through water. I gave you that example of skipping rocks, also going faster through steel or iron. Water, it actually goes 4 times faster, which you'll see in the notes there, and on steel or iron, it goes 15 times faster. I've never tried this, and I'm not encouraging you to do this, but supposedly if you take like a hammer on a railroad track and you and your friends are like 100 feet apart, when you hit a hammer on that railroad tracks, you'll hear 2 different distinct sounds. You'll hear the sound that's coming directly through the air, and also the passage of sound through the steel. And the steel should get there significantly faster. The math tells us basically about 15 times faster. So sound waves alter in different frequencies, stuff like that. Now one thing to keep in mind is also that different things that sounds move. That sound moves differently than, by comparison, light. So you see this light up over top of my head. Now, anybody have an idea how fast light moves? It's about 1 million times faster. So the true number is about 186 million miles per second. So we were talking 1,130 feet per second. This is now moving light. Everybody who's watched Star Wars or Buzz Lightyear, talking about light years and the speed of light. Sometimes they'll talk about how a planet explodes or something we're seeing and it's like 3 light years away. Light moves at least 1 million times faster than sound, and we'll get into that comparison here in just a second. Things like electricity. Electricity, obviously, this is a tech class, so a lot of things that we're going to do, your keyboards, your microphones, everything has to plug in somewhere, has some source of electricity, your lights, your video walls, all those things like that. Electricity moves much closer to the speed of light, just based on some basic efficiency factors as we move forward. Now, a couple of things to think about, though, is we see and we experience this. Sound is really not that fast. 1,130 feet per second is relatively fast. However, when we compare that to light, and we compare that to electricity and stuff like that, it's relatively slow. And we can experience that and see that in several different ways. Anybody know what this picture is of?
It's breaking the sound barrier.
That's right. Can you say it one more time for us, Harrison?
It's breaking the sound barrier.
Yeah, so this is a military jet airplane, and you're seeing it, what we refer to as breaking the sound barrier. You may have, if you've lived close to a military base anywhere, you may have heard what they refer to as a sonic boom. You may have heard terms like Mach 1 or Mach 2, or sometimes when we have a space shuttle up, they'll talk about that it's moving at Mach 15 around the Earth or something like that. All of those terms are referring to the concept of the speed of sound. That 1,130 feet per second number I gave you just a second, that translates to right about 770 miles per hour. If you were going to do the math on that, it's really pretty easy to do. If you take that 1,130, we know that that the distance for a mile is 5,280, right? 5,280 feet. And we also know that each hour has 36 seconds, or 36,000 seconds, right? 60 minutes times 60 seconds, 36,000. You start doing the math pretty quickly. So you can realize that that plane, when that picture was taken, was breaking the sound barrier, which is representative to close to about 770 miles per hour. Now, I'm guessing I asked this question, has anybody ever broken the sound barrier? Anybody military, never had a chance to be on Top Gun 2, weren't filmed as an extra? All right. Anybody know how fast your typical jet airplane will go? The pilot comes on and says, we're traveling at 30,000 feet at a speed of, anyone? Any guesses? Probably faster than 100, right?
Is it 500?
Yeah, it's usually 500, 550, depending on winds and stuff like that and jet streams. You'll notice sometimes if you've ever taken a long flight going east as opposed to west, I think west is actually a little bit faster. It's like when you're looking at the round trip times on flying, like if you're going to go to Asia somewhere, your west coast traveling, I think I said that right, when you're going towards the west, it's a longer flight than going east. What about cars? So we know that our speed limit is 70. Some of us kind of keep to that, right? So that's not very fast compared to 770 on our car here. What about race cars? Anybody know how fast like a typical NASCAR may go?
Around 200, right? Or like 220?
Yeah, something like that. And then you got your Indy cars, which are typically a little faster, 20, 30, 40 miles an hour faster than that. Anybody know what like the land speed record is currently in the world? I don't know the exact numbers, but I think it's somewhere in the 400 to 500 range as well. One of the challenges with cars or any type of vehicles is that you've got the friction of the ground and the tires that actually slows things down as opposed to the friction of a jet in air. There's much more friction as those tires are touching the ground, which is one of the greatest challenges if you read up a little bit on land speed records and things like that, is they're trying to make cars go faster and faster. So yeah, some of the fastest things. This jet is obviously going what we refer to as Mach 1, or the speed of sound. Our space shuttles and stuff like that, once they get outside of our atmosphere, they can go 15, 16, 17 times the speed of sound. So that's interesting as we consider those type of things. Now, why is this all important, and why am I sending you or shooting you a picture of a thunderstorm? There are several ways that we actually recognize and can notice this difference between the speed of sound and the speed of light. One of the best ways is lightning. Now, us that live here in California, we don't get to see and experience a lot of thunder and lightning. Caitlin knows about it. You get some good storms coming through Colorado for sure. So, and so what we're seeing in this experience is that when we see that lightning and when we hear the thunder, they happen at two different times. You've all noticed that, right? You may have had a weatherman at some time tell you, count the number of seconds from the time you see the flash to when you hear the boom, and divide by 5. And that'll basically tell you, and if we did the math based on the number I gave you, 1,130 feet per second, you kind of see why that works. So we are seeing visually the transfer of light at a much, much faster, 1 million times faster than the translation of sound to our ears. Anybody think of another example where it's very easy to notice the difference between sound and light? Anyone? What are we looking at? So fireworks, right? Everybody loved the fireworks. Looking forward to getting back to Disneyland, and so you can see the end of the night fireworks. 4th of July, all those different times that we do fireworks. That's another one. So we see the flash of light, but it may take maybe a second or a couple seconds until we actually feel and sense or hear those sound pressure waves moving at 770 miles per hour to get to us, right? One more example, you may have noticed this. One of my favorite places, oh, I had a picture, here it is. One of my favorite pictures here, everybody know what that is? Anyone? Any baseball fans recognize that one? Harrison, I saw you nod your head. Whose home field is that?
I'm gonna guess the Dodgers.
There we go, Dodger Stadium. They're playing games, right? But they got empty stadium. So, have you ever noticed when you go to the ballpark and they play the, da 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 da, the charge, the whole thing? Have you ever noticed that if you look across, or even when they do the wave or they're clapping, up, rhythmically clapping, you kind of see that people are clapping at different spots sometimes, or they're cheering, or they're raising their hand. Have you ever noticed if you're sitting in the outfield bleachers and the crack of the bat and you see the runner already running, but you hear the crack like a second or two later. Again, all examples of the passage of light as opposed to relatively slow sound. Now, why is this important in worship technology? There's a point to all of this. We deal a lot with sound, obviously. We also have sometimes play in rooms that are big, maybe not as big as Dodger Stadium. You may have a chance to play at something like that at some point. But we run into a concept referred to as latency. Now, you talk about latency a little bit with wireless networks and all kinds of stuff. Even Zoom has a little bit of a latency to it. So our radio stations, what the radio DJ is saying, we maybe takes a couple seconds to actually get back to our car or to our location where we're listening. But because sound travels at a different speed as opposed to electricity, those could reach your ears at different times, right? So in a big baseball stadium, you will notice that to avoid a lot of latency, they will add lots of speakers in different locations. Now, if you're in a bigger church, you may have noticed this as well. So they may have speakers that are up close to the stage, and they may have another set of speakers that are maybe 75 or 100 feet farther back. Everybody had a chance like to be to Angela's Temple. You ever gone to an Angela's Temple event? The Mother Church Foursquare? So they've got those. Harrison's nodding his head yes. So other big churches maybe that you've had or opportunities you've been, or you maybe have gone to a big concert at Staples Arena or different locations, stuff like that, you'll notice when we get into bigger sound systems, they'll have more and more speakers, usually farther and farther away from the stage area. So there'll be a series of speakers that are right up close, and then other speakers that may be a farther distance away. And that's all the reason of why they're doing that, is because they can use electricity to get the sound wave to you in the back of the audience much, much faster than waiting for the sound wave to go from the front of the stage. Also recognizing that as those sound waves are much, much stronger up close, so if I scream in your ear, you're going to really, really notice, as opposed to me screaming and you're 20 feet away from me. There's a major difference of that. And that'll be our next term as we get into amplitude here in just a second. Questions? Is that kind of making sense? The idea of latency? We also run into latency when we get into recording technology and stuff as well. Some of you may have noticed if you're running like Pro Tools or something like that. Sometimes when you're recording, there could be a little bit of a latency between like when you're singing, when you're playing guitar. And there's oftentimes preferences and menus and stuff like that that you can adjust to get your computer to run a little faster, a little more smoother to be able to capture things like that. So dealing with latency. All right, let's talk about amplitude. Amplitude is the fancy word, but of course you've heard the term volume, right? Or how loud or how soft something is. That's what amplitude is. Amplitude refers to the strength or the intensity, you might say, of a sound wave. We also use words like volume, loudness. Sometimes you'll also hear people talk about sound pressure level, or SPL. The technical term that scientists use is called decibels, or dB. And so you'll see that on tech terms and tech sheets and stuff like that. That refers to the relative quantity based upon a ratio for sound pressure levels. So let's keep a few of these in mind just so you can get a sense of how loud something may be. The red line here represents a low amplitude, so you'll notice the lines aren't going near as high. On this graph, it just says 20 or negative 20. The green lines are going a little bit louder, so they're going up to 60 and negative 60, and then those blue lines are going all the way up to 100. The red line would be relatively soft, or not as loud, low amplitude, all the way to the blue line, which would be considered high amplitude. By comparison, here's a little chart. So our ears should be able to start hearing quiet whispering, but notice whispering starts about 25 to 30 dB. There are very few places in the world that you can actually go and experience 0 dB. Anybody know what you would call 0 dB, or what the technical term is for a room that can produce 0 dB? An anechoic chamber. So if you look up anechoic chamber, there's a few of them out there. Typically, they use them in the audio industry for like testing speakers. It's the most accurate, speakers and microphones. It's the most accurate and easiest, best way for them to test audio equipment and things like that. But I've been told by people that have actually been in anechoic chambers, it's actually very, very unsettling. It's so quiet that like you can hear your heartbeat. You can feel your eyes, flickering. I mean, just stuff like that we don't even notice just based on the sounds that are around us. So whispering could be 20, 25, a quiet office, 50. You may notice with your dishwashers at home, they'll rate them on a dB scale on how quiet they are as opposed to how loud they are. The upper end of the spectrum here, talking about 120 or so, they'll refer to that as the threshold of pain. That's the spot of me screaming in your ear or a loud jackhammer or a jet airplane. You're going to want to put on ear protection. You may have heard of an organization here in our government called OSHA, O-S-H-A, and they have all kinds of standards like 85 dB for 8 hours and stuff. So if you ever worked in a factory or had the opportunity to work around that, there's certain safety standards you have to abide by, and wearing ear protection and stuff like that. Again, your ears are very, very valuable, so just always keep that in mind and protect them. Any sense of what a local church scenario might sound like as far as amplitude? Anyone? Some churches at the front soundboard will have a little device type of thing. Everybody's seen those? And they'll show it to an usher as somebody comes up that complains. It's only usually somewhere between 80 to 100. 80, 85 is usually relatively happy. People start complaining once you get above 90, 95. Also keep in mind that amplitude and decibels are a ratio. Again, this is more math and science. Do you know that when we talk about earthquakes, and there's like 1,000 times difference between an earthquake that's a 5 as opposed to a 6, that they exponentially increase at a rapid rate just as they exponentially decrease at a slower rate. So a 4 as opposed to a 5 on an earthquake may say, oh, it's no big deal. But it's actually, by the time you get to that 5, it's like 100 or 1,000 times stronger. Same thing with amplitude and with decibels. I think it's every 6 decibels represents a 50% increase. So there's a big difference between 90, 95, 100 dB as we get really, really loud in different environments. Questions? It's all making sense? All right, let's jump into our next term. Frequency. Frequency is at the rate at which a sound wave is going to repeat itself, determining the note, the pitch of a tone. So we have a term which we refer to cycles per second, which you can see on the screen here. Also, sometimes you'll hear named after the famous German physicist Hertz, H-E-R-T-Z, as opposed to Hertz like it hurts my ears. All of these refer to how quickly that sound wave is replicating. Now, it's important for me to say at this point, we're not talking about the speed of sound here. The speed of sound is constant, right? It's at 1,130 feet per second. But what we're saying is that if I were to play on the piano a very high note, those sound waves, and I'll get to the math here in a second, are very, very fast, as opposed to anybody that plays the bass guitar, which is on the other end of the spectrum, or the low notes on the piano. Those sound waves are moving at 1,130 feet per second, the same speed. However, they are much longer, and there's fewer cycles per second, and I'll explain that as we move forward on that. Our ears, our human ears, have the ability to hear from what we refer to as 20 cycles per second, or 20 hertz, all the way to 20,000 or 20 kilohertz. So 20 cycles per second all the way to 20,000 cycles per second. Now, interesting fact, your pets and animals, anybody have a dog? You've heard of dog whistles, right? Or the concept of dog whistles. So dogs have the ability to hear beyond 20K. So we're used to there. So our dogs can respond when we blow that little dog whistle. It drives the Chihuahua crazy. It's because they're hearing the spectrum that's outside of what our ears can hear. They also say that animals like elephants can hear below, and they've theorized that that's why some animals and stuff can respond to earthquakes, seismic activity, and stuff like that, is because they have the ability to hear below that 20 cycles per second. I'm going to play some sound waves for you for just a second, so we'll just get a sense of what that looks like. For point of reference, for those that play piano, your middle C is about 250 cycles or 250 hertz per second. So that sound wave, as you hit that note coming off the string, is cycling in the air at 250 times every second. As you get higher, it goes even faster. You get lower, it gets even slower. Again, all at the same speed. That audio spectrum of 20 hertz to 20 kilohertz represents about 10 octaves on the piano. Now, we all know that the piano only has 88 keys, so just over 8 octaves. So if you could imagine the notes, we should all be able to hear the notes that are on the piano, but 1 octave higher and 1 octave lower. Also recognize that chances are that your hearing is probably better than my hearing. We all have a natural, as we get older, we have a natural decrease, especially on our high range. They say newborn babies can hear really, really, really well up to that 20 kilohertz. And oftentimes we'll be responding to things that may be generating those sounds that the adults in the room can't hear. I find that my hearing typically drops off pretty strong by about 15, 16K. I'll be interested to hear when I play a couple tones. Also recognize when we do listen to that, it is kind of piercing. It is a little hard to listen to. It's kind of surprising. Most anything above about 10K is pretty shrill as you're listening. Now, in audio world, we'll kind of develop those. You may have heard about, if you had on your guitar, you may have a slider that says low, or on your car radio where you can adjust the mids or the highs. And those often fall within certain decades. So if we go all the way from 20 hertz on the very bottom, our low end may be anything from 20 hertz to 200 hertz. Our mid-range may be 200 hertz to like 2,000. And then our upper range could be everything from 2K or 2,000 to 20,000 cycles per second. Each octave represents a 2-to-1 ratio. So I gave you that example again, a middle C is 250. If I move up 1 octave to the next C up, that frequency is about 500. If I go back to my 250 and I go down, I need a piano here to demonstrate this. If I go down an octave, if you cut 250 divided by 2, about 125. I keep going down the piano. It's just going to keep cutting it in half on every octave. Any of you ever play like trumpet or flute or clarinet, saxophone in high school band? No high school band? All right. My dad was a band director, so I kind of grew up around all that type of stuff, played trumpet all the way through college. Sometimes a piano tuner will come and they'll talk about A440. Anybody heard the term A440? Yeah, I see a few nodding head. Anybody have those little guitar tuners that you put on your headstock? And sometimes those will give you a number as well to keep your guitar in tune, right? So all of those represent different numbers or frequencies or cycles per second or hertz. It's all the same concept, recognizing that each one of those octaves is going to double. So as you can think about that, as we go up the keyboard, as we sing higher, as we move higher and higher on the frequencies, those are moving much, 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 much faster as opposed to the opposite end. Anybody play bass guitar? No bass guitar here? All right. The bottom string on a bass guitar, that low E string, is about 40 hertz a second. So it is vibrating about 40 times every second. And for those that play other instruments, you can look online. There's lots and lots of charts. We'll look at one here in just a second before we get into some listening. Let me find our chart here. So if we look at this, I just gave you the bass 4-string. Starts about 40, and the fundamental is going to be right about 400, it looks like there. So if you look about 7 or 8 down there, we've got guitar. I've talked a lot about piano, but guitar, your bottom string, that low E string on your guitar is somewhere around 75, 80, up to about 1.2K probably, 1200. There's a few other ones that are marked there. Notice the male and the female voice. Females have a higher voice typically. Here's another picture that we can use as well. The human voice in this picture, guys, some of us can sing down to about 110 hertz, where the top end may be closer to 1750 for somebody who's like a soprano singer. I'll show you a video, probably we'll do that in one of the next couple of weeks, actually the human voice and how that works. There are 2 muscles behind the bone. Guys, is our Adam's apple, right? And those, if you use infrared, you can see them vibrating and moving. Ladies, this is really interesting. Your vocal cords, or that little mechanism that's in there, is about the size of a dime. Dudes, you going to guess it's bigger or smaller? What do you think, guys? Erwin, what do you think? Is your vocal cord bigger or smaller than Caitlin's?
Bigger.
That's it. Yeah, it's bigger. So it's probably more the size of a quarter. And we all have that terrible P word, right? When we're about 13 or 14, right? Call it puberty, right? And that's what's happening. Is that for the guys, your voice is cracking is because those muscles and that bone within that little segment, your Adam's apple, if you run it across, you can feel it. That's what's happening. So I'll have a really cool video where they take a thing down the nose and they go through and endoscope, whatever they call it. And if you put black light on it, you can see those vocal, right? Anybody know the difference between speaking and whispering? What's the difference on that mechanism?
During whispering, your vocal cords aren't you're not getting that vibration, right?
That's right. That's right. Yeah. Yeah. I think it's humanly impossible to whisper sing, right? Because singing really, it creates that fundamental as opposed to just the speaking voice. Yeah, that's good. That's good. So we'll do that next week. You'll get a sense of be able to do that. Again, those octave representations represent a 2-to-1. So as I go up the piano, every octave it doubles. As I go down, it goes in half. The higher frequency is going to mean higher pitches, and then lower frequency is going to mean lower pitches. I think I got one more picture here for you from Sweetwater. We'll look at this one probably a little bit later. You see, let me get my telestrator working here. Up on the top part, we've got the bass guitar, different instruments that go all the way down. And this gives us a sense of the different characteristics. So there's what they refer to as weight of the bass guitar. Well, if you look down here on our chart, I told you that the bottom note on a bass guitar is about 40. So yeah, there's a lot of weight there. But there's not, the sheen is kind of up here, which you're not going to really hear a lot of that, so on different spots. So that's a good chart that we'll get into later as we go through the semester. All right, I'm going to play some sound waves real quickly for you. The first one I'm going to start with is going to be 250 hertz. I gave you this example a few minutes ago, that 250 hertz is basically the middle C on a piano. I'm going to play sound waves at 250, 500, 1000 or 1K, 2K, 4K, and then 8K, and we'll just get a sense of what you think on all of those. So here's 250 hertz. Everybody hear that? Let's do it one more time. Let's do the next one, 500 hertz. Now you probably recognize right away that this is a lower note. This is higher. You also could probably recognize that they would be referred to as octaves, right? You may have noticed, like if somebody said, sing high, sing low, right? Those notes are basically the same. If you ever had a chance to sing in choir, typically the girls are going to sing out the higher note, the guys are going to sing the lower note. And many times we don't even recognize that the guys and the girls are singing in different octaves in a choir situation. Anybody sing in choir before? All right, we got a few choir singers. Awesome. And that all goes back to that size of the human voice as we go through there. Let's listen to another one. This is 1K. Let's do the next one, 2K. A little more piercing, right? A little harder to listen to. All right, we're going to go big or go small. Here's 4K. And finally, 8K. Everybody still have their ears? Now, 8K, if we think about it, it's not really that high compared to the 20 hertz to 20,000 hertz that I talked about for perfect human hearing. We've still got an octave, octave and a half that we can go higher. So when we really get into audio and stuff like that, there's really not a lot of purpose for that extra high sheen or that really high whistly stuff. It just starts hurting. One of the things you'll discover with great audio technology is that kind of the better the quality of what you're representing, people will listen at a higher volume, higher quality sound, as opposed to low quality sound. As it gets louder, it just hurts. We've all been to a concert, and the next day our ears are kind of ringing, and it's just like, it just didn't sound good. And we've all had, experienced something like that as you move forward. Any questions about frequency? If you want to, I took all of those tones. This is back to the Moodle side here. I took all those tones from a website called audiocheck.com, .net, sorry. And you can do all kinds of testing and try different things. There it is, yeah. It's a free website that you can access on things like that, so you can listen to that. If you want to have some fun and play with some different frequencies and try some different things, that's all available for you. So you'll also find sometimes if you play higher or lower stuff, that sometimes like the speakers on your laptop may not be able to represent that, or they can't play them back, or your headphones, things like that. Certain microphones, which we'll get into next week, don't pick up certain frequencies. Like they can't pick up the high end. They can't pick up things lower than certain frequencies as well. So that's all part of the technology that will go together. All right. Our next term as we move forward, wavelength. Anybody know what wavelength refers to? So wavelength is the distance it takes a sound wave to complete a frequency cycle. On our picture we had there just a second ago, let's go back to that. Are we seeing that? Wavelength refers to the time it takes for one cycle. Now we don't have our axes that we had before, but you'll notice that going from a high point, a cycle going to a low point, and then coming back to the high point as well on that sound wave represents one wavelength. So another way to say that, if our middle C note is 250 cycles per second, there would be 250 different wavelengths all equally spread across that. And we'll get into that formula here in just a second as we break that up. We'll notice here that wavelength is going to vary by inverse proportion. So again, high frequency notes are going to have much shorter wavelengths, and low frequency notes are going to have much longer wavelengths. Notice the ones on blue are much shorter. They're higher frequencies. These are the notes at the top of the piano. The red ones are much longer on the wavelength, and these are the notes more on the bottom of the piano. When we discuss this, we have two different formulas, and this is something you're going to want to keep track of and learn as we go through the semester here. Our first formula, talking about wavelength equals the speed of sound, and I gave you that, divided by the cycles per second, or frequency, or hertz. So again, wavelength, which is a measure of distance, this is going to be in feet, is going to equal to the speed of sound. You all remember the speed of sound, right? 1130 feet per second. So 1130 is always going to be our key number as we do this together. I'll get the calculator in a second. Divided by the frequency. So for instance, if I ask you the question, what is the wavelength of the middle C note on a piano? We would be able to do that, relatively simple, by simply taking 1130 divided by 250, and our answer would come somewhere about 4.52 feet. So that means, as when I play that middle C on the piano, the sound waves that are being generated from the string is between 4 and 5, 4.52 feet long. We'll do a few more of these calculations as we go along, but just to give you a sense of kind of what that means on that. Again, wavelength is equal to the speed of sound divided by the frequency. Why is this important? Well, think about this. We've mentioned the bass guitar before. So a bass guitar, the bottom string, that E string, is 40 hertz a second. So if we take 1130 divided by 40 hertz, that sound wave is going to be 28.25 feet long. 28.25, almost 30 feet long. Now, when you're playing bass, typically you're going to stand close to your bass amp, right? Have you ever noticed or experienced where the bass player is like, everybody's complaining, the bass is too loud, it's too loud, it's too loud. You know, the old lady in the front row is complaining. But the bass player is like, I'm happy as a clam. This is great. I'm fine. I can't barely hear myself. Can I turn it up a little bit? This is exactly what we're talking about. So the sound is coming from that bass amp or from the guitar on the stage at 770 miles per hour, 1130 feet per second. Those wavelengths, 40 cycles per second when they hit that bottom note. But every one of those waves is almost 30 feet long. So the high point and the low point could be 14, 15 feet in front of the bass player, right? So what the bass player is experiencing is a very low amplitude or lower volume than the audience when it gets 15 feet off the stage. Does that make sense? Now the other end, like the high notes on the piano or the piccolo, like it's never going to be an issue because those are they're less than an inch. They're so short on those wavelengths. Harrison, go ahead.
Is that because, so you were talking about how it was three-dimensional, the wave, right? So if is that because like the bass player is closest to where the sound's being projected, that the wave is smaller and it would get bigger and then eventually collapse and repeat the wave?
Yeah, exactly.
Okay.
That's perfectly it, yeah. Any other questions? You've probably experienced this one as well. In fact, I noticed this. I was driving over to my wife's office here this morning, driving in traffic, and all of a sudden you hear a low rumble, or somebody's got a subwoofer in their car, right? And it's very disorienting because you kind of don't know where it's coming from, right? Some guy is thumping some R&B and making a lot of noise. Anybody have a thumper, a 12er in there, or 15 in their car, in their trunk? You'll also learn that low frequency is very what they'll refer to as omnidirectional. So it goes in lots and lots and lots of directions. Think about taking a big stone and dropping it into a pond. You're going to get lots of splash in every direction, up, down, left, and right. As opposed to higher frequency notes, which are much more pointed and directional in their characteristic as we move forward. So just a couple examples and things to think about when we think about wavelength. Our final term for today is period. And the formula we're going to keep in track with period is 1,000, and the 1,000 refers to milliseconds, which is basically 1,000 milliseconds within 1 second. Because again, we're talking about cycles per second divided by the frequency. Now, wavelength and period, people get lost on this really, really quick. Wavelength is a measurement of distance, where period is a measure of time. So period is referring to the time for one wavelength, or 1 cycle per second. So when we look at our picture that we had a few seconds ago, we could swap this wavelength title here for period, and the difference between, are we talking about time or if we are talking about distance. Same thing on period. It has an inverse proportion. So a high frequency note is going to have a much shorter period, and a low frequency note is going to have a much longer period. Now, again, we are talking about time, and don't get confused that the speed of sound and all of this is staying the same. Those low frequency notes, 20 hertz, the low notes on a piano, the bass guitar, those sound waves are traveling at the same speed as the piccolo, from the piccolo flute. But their periods and their wavelengths are going to be significantly different as we go forward on that. Questions? Go for it, Harrison.
Can you give me an example of that?
On period, yeah. So the timing, and we'll get to this, so let's use our formula that we've got here, right? And we'll do a few of these together. So if I have a sound wave, we'll go to that back to our middle C. So 1,000 divided by the middle C on the piano, which is 250. That's going to be about 4 milliseconds to make that. So 4 1/100ths of a second. Let's go up an octave. So 1,000 divided by 500, 2 milliseconds. Again, it's still moving at 1,130 feet per second, but it's replicating at a much faster rate. We go up another octave, 1,000 divided by 1,000, 1 millisecond. So each one of those sound waves is happening or is cycling much, much, much faster. Does that make sense? And when we look at these formulas, and we'll do some questions and stuff together, always keep in mind, are we looking for distance, or are we looking for the passage of time? Like how long did it take to get from point A to point B on that? Questions? Any questions for you guys so far? Awesome. All right, let's take 5 minutes. Take a 5-minute break, and I will get you back right at 2:50. I'll give you 6 minutes. Go.